So another approach might be to try to conduct a hypothesis test. So perhaps there's this specific value that you might be concerned of if it was above that value. So researchers in this case set it at 3.5 micrograms per wet gram. And perhaps if they have evidence to suggest that it's above that particular value, maybe that's considered dangerous and you would implement some kind of environmental plan or political action, put that into movement if you had evidence to believe that it really was greater than that value. So we're going to go through and conduct a hypothesis test with 95% confidence for the average mercury content of the dolphin muscle. So just to sort of clarify, the average mercury content of the dolphin muscle, that's our population mean mu. Okay, so we're interested in what the average mercury content is for all dolphins, really. Okay, what we've done is we've conducted a sample of 19 dolphins. We can see that from here, right? There's 19 dolphins and they had a sample mean of 4.4 and a standard deviation of 2.3. All right, so we better start by defining our null and our alternative hypothesis. So the null hypothesis is always going to be sort of this value that we're interested in, okay? And it's always going to have an equal sign. So the null hypothesis in this case is that the mean mu, the mean content, is actually 3.5, okay? Or maybe something less. And our alternative here is that the mean is going to be greater than 3.5. What you'll notice is that these hypotheses are always done about mu, the population parameters. They're not being done about x bar, the sample mean. Okay. Next thing we might want to go through and do is work out our test statistic. Okay. In this case, because we're testing about one mean where the standard deviation is unknown, our test statistic is x bar minus mu naught, and mu naught is this thing here. Okay. This is mu naught, the sort of critical, that value that we're sort of concerned it might be above or below, divided by sigma s over the square root of n. Okay, so again, we've got our estimate minus our hypothesized value under the null divided by the estimated standard error. Okay, so I'm going to plug in values. In this case, I've got 4.4 minus the 3.5, that's the hypothesized value under the null, divided by 2.3 divided by the square root of 19. Okay. So when I worked that all out, plugged that into my calculator, I got 1.70, if I round it to 3 decimal places, 6. Okay. Now my test statistic is going to follow a t-distribution with n minus 1 degrees of freedom. So in this case, my degrees of freedom is going to be 18, 19 minus 1. And so I'm just going to draw a little picture just to sort of remind us what is going on here, right? We've got our t-distribution, okay, with 19 degrees of freedom, okay? There's my test statistic. It's going to fall on there as a particular value, the 1.706. And so the p-value, the probability of observing the test statistic we did, given that the null hypothesis is true, is going to be the area in this right-hand tail. I may want to go through and just look. The alternative hypothesis here is that the mean is greater than 3.5, which means we're looking at the shaded region to the right. If this had been less than 3.5, we would have done the area to the left. And if this had been not equal to, right, then you would have needed to take that area in that tail and multiply it by 2. But in this case, we've got a one-tailed test. It's a greater than sign, so we're just going to look at the area to the right. To work out that p-value, that area in that right-hand tail, I'm going to use R. The code that I'm going to use is I want the probability or the area, so it's a p, and it's on the t-distribution, so t, that's our code. I'm going to feed in the value of the test statistic, 1.706. I'm going to give it the degrees of freedom, which is, oops, I wrote 19, here, and it should have been 18, right? And so my degrees of freedom should be 18, and then I'm also just going to type in that the lower tail should be false, right? Because we want the upper tail, we want the area to the right. So when I plug that into R, PT 1.706, 18 lower dot tail is equal to false, I get 0.0526. So I'll just write that in here. The p-value in this case is 0.05, and I'll just round to 3 decimal places, 3. Okay, so that's my p-value. Now, in this case, you always want to take your p-value and compare it to your alpha. So we've got my p-value, which is 0.053, okay? And I'm going to compare that to my alpha. Now, in this case, I wanted to do it with 95% confidence, so 0.95 confidence. So alpha in this case would be 0.051 minus that. And so from there, I'm going to take and compare these two, right? So we have a 5% chance of observing the test statistic that we did, given that the null hypothesis is true. And 5% is kind of our cutoff range. And in this case, our p-value is just slightly more than what our alpha was. And if the p-value is larger than our alpha, then we are not going to reject the null hypothesis. Do not reject H naught. Okay. I also want to just reiterate here, we either reject the null hypothesis or we do not reject it. I'm definitely not going to write here that I'm going to accept the null hypothesis. All this says is that we haven't been able to gather enough evidence to be able to say that the alternative hypothesis is true. So we do not reject H naught. And if I wanted to sort of write a concluding sentence, I could say that there is not significant evidence to suggest that the true mean mercury levels in the dolphin muscle is more than 3.5 micrograms per, what was the units? Wet gram. And usually what happens whenever we use this word significant, right, we usually want to specify the p-value or specify the level of confidence that we made that decision with. So I usually write the p-value. So the p-value is 0.053. Okay. All right, so in this case, you know, we expect some random variation here in the x-bar, and so they sort of are thinking that, well, maybe we just happened by random chance to gather a bunch of dolphins that had slightly higher mercury content, but we really can't say that the true mean is different from 3.5, at least at that particular level of significance.